Hi, welcome to the second lecture on CFD. In this lecture, we will first discuss about the use of CFD in modern day industries. And in order to do this, we have to explain the different phases that lead to the use of CFD to optimize a product. This is what I would like to call as a 50,000 feet view. We will also go over some applications to give you a sense of the wide range of problems that can be solved using CFD. When it comes to CFD software design, one of the major requirements from any company that uses CFD is that its employees should be able to use the CFD software quite easily. In this process, a lot of details is hidden from the end user. This outcome has manifested itself in a negative way by making students think that it is very easy to set up a CFD problem. A common misconception seems to be that CFD is all about learning to simulate flow through a pipe in ANSYS Fluent. In order to prove that setting up a CFD simulation is a non-trivial process, we will discuss the steps that is involved in simulating a popular thermal system, the internal combustion engine. Once we do that, we will be ready to understand what CFD is. We will look at the Navier-Stokes equations and also discuss how to solve it using numerical techniques. Okay, so let us try to understand the process of product optimization at a very high level. In this case, the product that we are going to optimize is a heavy-duty truck. Before optimizing the truck, don't you think we need to ask the following questions? First of all, what is the problem and why are engineers spending their time to solve this problem? And more importantly, why are they relying upon CFD to get the solution to this problem? Okay, so let me add some clarity here by explaining about this problem a little bit more. In the US, heavy duty trucks account for 20% of the fuel consumed in transportation. Now you need to remember that these trucks account for only 4% of the entire road transport vehicles that are present in the US. This means that last year 1.4 barrels of oil was consumed by these trucks, out of which almost 1 billion barrels of oil was used to overcome just the drag force. This huge wastage repeats itself year after year and is what drives significant research to reduce the drag coefficient. Now, the reason why it is an aerodynamic problem is because of the speed at which these trucks travel. When a truck increases its speed from 50 to 70 miles per hour, the amount of horsepower it consumes goes from 70 to almost 180. That is more than a factor of 2. This is because the drag on the vehicle is proportional to the square of the velocity. So you cannot reduce the velocity, but you can try to reduce the drag coefficient. Now, how to reduce the drag coefficient? Well, to do that, we need to first look at where the drag is high. Drag is caused by the presence of high and low pressure regions in the fluid flow. With respect to a truck, with and without aerodynamic fairings, you can see the regions that are responsible for drag and where you can actually design and develop aerodynamic solutions. The next obvious question that you need to ask is, how are these drag forces measured? Well, there are quite a few options. Wind tunnel testing, road testing, and also CFD. Let us compare these methods and try to understand their advantages and disadvantages. Wind tunnel testing is quite cheap, but is not representative of the real world physics because the conditions inside a wind tunnel are very well regulated. Road tests are quite accurate, but they are super expensive and time consuming. A single road test can cost as much as $20,000, and different countries have different standards that they use to conduct these tests. This is where CFD is all of a sudden a great option. It is dead cheap when we compare it with the other solutions, and it can provide results in a quick manner. The drawback is that you need to always validate it and you cannot trust it 100%. The main reason is because there are so many parameters that can be tuned inside a CFD solver, and companies spend a lot of time in finding these constants, which eventually becomes their intellectual property. One way the ideal parameters are discovered is by performing validation studies. In this slide, we are showing you an image of the generic conventional model truck. This is a simplified truck that was tested in a wind tunnel and a large amount of data was gathered. So now you can do a CFD simulation on this truck and you can compare the results from your CFD simulation against the experimental data to validate the CFD model. This process is repeated for several different configurations to finally establish the right CFD parameters. Once a reliable CFD model is in place, the engineers can modify the geometry as required and keep running the CFD simulation. When an optimal design has been found, they can run experimental testing on that particular design alone. This is how CFD plays a role when it comes to optimizing drag coefficient. It is not a standalone tool. It would be great if it is, but it is just a testing methodology that helps design engineers get an approximate understanding of the effect that their design has on the aerodynamic performance of the truck. Here's an image that shows the evolution of the aero panels over the last several years. Engineers keep learning and perfecting their craft, which leads to slow but steady improvements in the final design. Now that we have proved the usefulness of CFD, let us look at some applications of it. CFD is used for aerodynamic design and also for designing fluid containers to minimize the effect of oil sloshing on the driving performance of trucks. Hypersonic nozzle designers use CFD plus combustion modeling approach to improve combustion stability by optimizing the mixing characteristics of air and fuel. CFD is also used to design and test mechanical heart valves. CFD is an obvious choice here because you cannot test these devices on a human directly. Before clinical trials are started, a large number of numerical simulations are performed to establish confidence in the proposed design. I hope at this point you realize that CFD plays a critical role and setting up a CFD simulation is not a trivial task. To drive this point even more, let us take the example of an IC engine simulation. First, you need to take care of the geometry configuration. Here, you clean the CAD model and then split it into meaningful regions. This is done to make sure that you can assign suitable initial and boundary conditions. Then we need to take care of thermophysical properties for both the gas and liquid phase. If the physical properties are not accurate, then that can lead to completely wrong results. Standard property databases are used in these calculations, and choosing the right equation of state is also equally important. The next important step is the meshing strategy. The mesh needs to be refined enough to resolve the flow through the intake and exhaust valves. The right mesh size is required to resolve the flame front, and the right mesh size is also required to get the wall heat transfer. Finally, you need to choose the right equations to solve. Apart from the basic conservation equations, a lot of different governing equations are solved to get the required results. To simulate turbulence, the right choice of turbulence model needs to be made. Popular turbulence models include K epsilon, K omega, and K omega SST. In addition to that, if fuel spray is being simulated, then the appropriate spray breakup models and spray vaporization models needs to be used. For getting the correct combustion characteristics, the right combustion models needs to be chosen, and to get the emissions right, the right emission models needs to be chosen. This is why a CFD analyst should be a subject matter expert and also have knowledge about fluid mechanics, numerical analysis, and CFD. So now, what is CFD? CFD stands for computational fluid dynamics. At the end of the day, it refers to simulating fluid flow using a computer. We solve the fundamental equations that govern fluid flow, and in certain cases we employ simplified math models to capture certain physics without spending a lot of computational power. All these equations are solved in a discrete domain called as the computational mesh. The results obtained from a CFD simulation can be used to compute engineering quantities. So let us take a look at the equations. Here you are looking at the continuity, momentum, and energy equations. Continuity equation takes care of mass balance. Momentum equation takes care of momentum balance. The momentum equation is basically the Newton's second law applied to fluid flows. Then we have the energy equation that takes care of energy conservation. Now do not worry too much about these equations. Over the duration of this course, we will familiarize ourselves with them and become more comfortable. Now historically, the Navier-Stokes equations would refer to only the momentum equation. But now in this day and age, some CFD engineers refer to all these equations as the Navier-Stokes equations. Alright, now let us take a look at the terms in these equations. The first term is the time derivative term. This term represents the time rate of change. So in the momentum equation, it represents the time rate of change of momentum, and in the energy equation, it represents the time rate of change of energy. When we talk about solving this equation, this is the term that we're trying to solve. When we solve this equation, we are basically able to find out how the velocity, pressure, and density at any given point in the fluid domain is going to change as a function of time. The second term that you need to understand is the convective term. The convective terms are responsible for the fluid flow. If the convective terms are not there, the fluid is not going to move around the domain. The dP by dx term is also called as the pressure gradient term, is responsible for capturing the effect of pressure in the domain. Finally, you have the diffusion terms. These terms are responsible for momentum diffusivity and shear. We will explain these terms in more detail in upcoming lectures. And finally, when you take a look at the energy equations, you see that you have similar terms. You have a time derivative term and several spatial derivative terms. At this point, we are not going to talk about these terms, and when we derive the governing equations, we will be paying attention to them. So the main takeaway about these equations is that they are coupled and they are nonlinear, and that they cannot be solved analytically. The fact that it cannot be solved analytically is the primary reason for the existence of CFD. So how do we then solve it? These equations are first of all continuous. That is, they are valid at each and every point in time and space. However, if we convert these equations so that they can apply on a discrete domain, then we can convert these PDEs into algebraic equation. This process is called as numerical discretization. This process introduces a lot of errors, but at least provides us a way to solve these equations. You might have already employed numerical discretization during your undergraduate studies to calculate the slope of the curve. For example, if we have a curve, then we can take 2 points that are spaced at a distance of h and then compute the derivative. This derivative is called as numerical derivative and is less accurate. If the value of h becomes smaller, the accuracy of the derivative computation increases. Now the interesting thing is that there are several options to compute the numerical derivative. However, not all of these options are valid and will work in every case. Figuring out which method would work is the whole point behind studying numerical analysis. Alright, so let us say that you are able to identify how to discretize each and every term. What is next? When we convert all of these equations into their algebraic form, we will end up with a system of equations, basically a matrix. If we solve this matrix, we can get the solutions to our governing equations and compute flow properties such as velocity, pressure, and temperature. Linear system solvers is a separate area of study and it involves a lot of math and patience. Oftentimes, people use third-party libraries so that they can solve these equations. Okay, alright, I hope this lecture gave you an overview of what CFD is and how it can be useful. Thanks for watching. Bye.